Hi everyone. Today we have who is a more postdoctoral fellow at MIT, and he's going to tell us about the reasoning about electrical resistivity through emergent symmetries and anomalies. Go ahead, Dominic.
Thank you very much for having me here. So I'm going to tell you about this work that I did with Cento at MIT, mostly described in these two papers. So just to briefly to explain how this talk is going to work, because this is a longer format talk, it was suggested I should, go a bit more into the background than I normally would. But I did want to first give you an overview of what the new results are that I'm going to describe. So I will begin with that, with the overview, and then I will go back and talk about the background, which will help to understand the technical details of the results. So let me begin with the overview. So the motivation is that really we would like to understand the physics of metals. And so there's this very famous theory of metals, Fermi liquid theory, where the low energy excitations live near the Fermi surface, and they're described in terms of quasi-particles with long lifetime. And although Fermi liquid theory is a very successful theory in many materials, there are also many materials which we see experimentally are not described by Fermi liquid theory. And so such non-Fermi liquid metals are still a subject of much study to try to understand what is going on there. And a very famous class of non-Fermi liquid materials is these doped cuprates, like YBCO. Is a very famous class because, for one thing, they host high temperature superconductivity. But there's a lot of interesting stuff going on in the phase diagram of these materials. So here's a typical phase diagram. So you have a superconducting dome. So I'm not going to say much about superconductors today, but we would also like to understand this strange metal regime that appears above the superconducting dome. So if you suppress superconductivity, for example, by a magnetic field, strange metal seems to go all the way down to zero temperature. So some zero temperature metallic state of matter that we need to try to understand, but it seems to be very difficult. Many people have tried to think about this, and no one has really come up with any satisfactory theory of this strange metal. It's certainly not described by Fermi liquid theory, and there are many signatures you can look at to tell you that. For example, resistivity, Fermi liquid theory predicts resistivity scale like temperature squared, but strange metals you see very clearly in the experiments for resistivity is T-linear. Linear in temperature. Okay, so this talk is not going to be about the solution to strange metals, but what I want to do instead is I want to kind of take a step back and say, let's focus on this issue for resistivity. What are general statements that one can make about resistivity without reference to a specific model or a specific theory? So instead of trying to come up with some theory that will predict everything about the strange metal or about other non-Fermi liquid states, let's just take a step back and try to make general statements based on general arguments about resistivity. And so that's the motivation for this talk, and then the rest of the talk basically will be about what general statements can one make about resistivity. So the general setup is, let's consider some quantum many-body system with a global U1 symmetry. And so there's an associated conserved quantity, which we will call electric charge. It doesn't have to be the real electric charge, it's just whatever the conserved quantity associated with this global U1 symmetry is. And then you can apply an electric field, by which I really mean just a background gauge field for whatever this global U1 symmetry is. And then you can compute the resistivity, which is the ratio of the current to the electric field. And so you could ask the question, what is the mechanism for this resistivity to be non-zero? Well, of course, if you have a charge gap, such as a band insulator or a Mott insulator, then the resistivity actually goes to infinity at low temperatures. But let's suppose we're talking about a metallic system. What causes the resistivity of a metal to be non-zero? So in Fermi liquid theory, the current is carried by these quasi-particles. So the resistivity must be caused by scattering of these quasi-particles. And the scattering could either come from disorder or it could come from Umklapp scattering, where the periodic lattice potential scatters the particles. So if we want to move on to non-Fermi liquids, the statement about quasi-particles probably is not true anymore. Non-Fermi liquids generally don't have these quasi-particle excitations. It's more like some strongly interacting quantum soup. So we can ask, what is the origin about resistivity? How should we think of it in a more general way about how resistivity goes in these systems? And so that's one of the questions I will address in this talk. in a general system, there could be some non-Fermi liquid. What are general statements that we can make about origins of resistivity? So it will turn out, and I will explain in what sense this can be made precise, that you can still attribute resistivity sometimes to disorder or sometimes to Umklapp scattering. But there is actually an additional possibility in non-Fermi liquids, which is that resistivity could instead be caused by critical fluctuations. And this is a mechanism that we call critical drag. And so one of the major goals in this talk will be to explain what we mean by resistivity caused by critical fluctuations.
Excuse me.
So, sorry, there's a question.
This picture, where are the superconductors?
Well, I mean, this picture is not supposed to be most general. I will say something about superfluids later on. Technically, we have a global U1 symmetry. We can't really talk about superconductors, but superfluids is the global U1 symmetry version of that. So I will talk about superfluids quite a bit later on. So maybe you can see how it works later.
Right.
So, okay, so we asked the question, what causes the resistivity to be non-zero? But maybe we should turn this question around and ask what would cause the resistivity to be zero? Because the reason why I say that it's helpful to turn it around is that if you do have exactly zero resistivity, it implies that the system supports dissipationless current. So the current that flows in an equilibrium state without degrading. So there's an equilibrium state with a non-zero expectation value of the current. But then you wonder whether this could ever occur. In fact, there's a theorem called Bloch's theorem, which states that the expectation value of the current is zero in thermal equilibrium. So this is not the Bloch's theorem that you see in Ashcroft and Moment about the lattice momentum. It's a different Bloch's theorem. And so this Bloch's theorem that says that the current is zero in thermal equilibrium, I think it first appeared in this paper by Bohm, even though it's attributed to Bloch. And then, but much more recently, there are some nice papers that have come out that have generalized the proof of this theorem into a most general context, for example, to lattice systems. So, I mean, it's a very general result as these papers show. So then you have to wonder, well, okay, if you have this theorem, then maybe you can never have dissipationless current. Okay, but we know that there are systems that do have dissipationless current. There are superfluids, for example. As I said before, I will say superfluid rather than superconductor only because I'm talking about systems with global U1 symmetry. So there's no Meissner effect or anything in these systems. So that's why I will use its terminology that we call it a superfluid. In any case, superfluids have dissipationless current, as everybody knows. That's the most famous property of superfluids. And another example of a system that has dissipationless current is that it's an electron gas in the continuum. So suppose we have some gas of electrons, maybe they're interacting electrons, but they're moving in the continuum, so there's no lattice or anything. And if they move at some drift velocity, then you maintain that drift velocity forever. So that's another system that has dissipationless current, electron gas in the continuum. So then you have to ask, how is this well-known properties consistent with Bloch's theorem that seems to forbid dissipationless current? So let's think about what exactly does Bloch's theorem state. Bloch's theorem is a really statement about this grand canonical ensemble state. So we have some conserved charge as well as the conserved energy. So the correct thermal equilibrium state would be this grand canonical ensemble state. And then Bloch's theorem states that for this particular state, then in the thermodynamic limit for some general Hamiltonian, the expectation value of the current is zero. So if you do have an equilibrium state with non-zero value of the current, it must satisfy, it must not be equal to the grand canonical ensemble state. So why would this occur? I mean, we all know the derivation of grand canonical ensemble in textbooks. It seems very general. Oh, a way to have an equilibrium state that is not the grand canonical ensemble state would be if you have an additional conserved quantity. So if you have some additional conserved quantity gamma, then instead of the grand canonical ensemble state, the thermal equilibrium state would involve an additional thermodynamic variable conjugate to gamma. So you would have this generalized equilibrium state. And so this generalized equilibrium state might not have zero current, even though the grand canonical state must have zero current. So that's basically the mechanism by which you can have a loophole in Bloch's theorem if you have additional conserved quantities that protect the current. So going back to these examples, an electron gas in the continuum has momentum conservation. So that's what protects the current in that case. Superfluid, the issue is a little bit more subtle, but there's some kind of conserved vorticity. I will come back to superfluids later on in the talk and make that statement more precise. So then you can ask the question, why is Bloch's theorem satisfied for this grand canonical state, but not for this generalized ensemble? I mean, they look almost the same, like what's the difference? And so in this talk, I will explain the answer to this statement. It's basically, the answer involves anomalies, which will end up being a very powerful way to think about these loopholes. But so that's something that I will explain in much greater detail later on.
Another question. Isn't it the persistent currents, thanks to Bloch theorem, are still vanish in the limit of a large size of the system? So if I take a ring, if I have an equilibrium state of a superconducting ring, then I think the current does vanish as you take the radius of the ring to infinity.
Well, not necessarily. I mean, if in the grand canonical ensemble state, it vanishes, but I mean, the current carrying state is not the grand canonical ensemble state. It's characterized by this generalized equilibrium ensemble, and this generalized ensemble is allowed to have non-zero current even if thermodynamic limit. So that's the difference. So it's protected by the symmetry.
But there's no other macroscopic symmetry in a superconducting ring besides energy and charge conservation.
There's no microscopic symmetry, but there are emergent symmetries that protect the current. I will explain that. Sorry?
Unapproximate. So there's no. This is not a stationary density matrix. Respect for the.
Well, emergent symmetries are not. I mean, it depends what you mean by approximate. I mean, if you're in the superfluid phase, the emergent symmetry is actually a very good symmetry for reasons I will explain. So, well, essentially in the superfluid phase, it is a exact symmetry, but you have to be in the superfluid phase. That's why we say it's an emergent symmetry. But maybe this will be clearer later on when I actually explain how superfluids work.
You have a metastable state, of course, right?
Well, it depends what you mean by metastable. I mean, it's extremely stable, in fact.
Very long-lived, but it's still metastable. It's not a,
No, can I interject quickly? The radius of your disk, the thickness of your disk goes to infinity, then the current will live forever.
Okay, so it's stable. It's metastable, and it's the lifetime goes to infinity as the radius. Okay, because
so if you take the right thermodynamic limit, persistent current lives forever.
Okay.
So all this, as I said, this is the overview. So all these points will be explained more detail later on. But for a moment, I want to ask the question of, suppose we have a system that has zero resistivity due to conserved quantities, because of this loophole Bloch theorem that I mentioned. How can we deform the system if you want to recover non-zero resistivity? So one direction would be you just violate the conservation law, whatever it is. So for example, in a Fermi liquid, the resistivity comes from disorder and umklaps, which are breaking the momentum conservation. So if you violate the conservation law by adding some interactions to the system, then you can recover non-zero resistivity. But there is another route to get non-zero resistivity, which is that you keep the conservation law intact, but then the density of conserved quantity undergoes critical fluctuations. It turns out that can also give you non-zero resistivity, and that's a mechanism that we will call critical drag. So as I said before, it's resistivity that's because of critical fluctuations. And so this is the sense in which it's a new kind of mechanism, because we're used to thinking about resistivity comes from violating conservation laws, as it does in a Fermi liquid. But this critical drag will be resistivity from a completely different origin, critical fluctuations. So let me just give you the lightning overview of how this works. If you have a conserved quantity, gamma, then, as I said, because of this loophole in Bloch's theorem, it can give you a infinite DC conductivity, zero resistivity, infinite conductivity. Another way to say that is that if you think about the AC conductivity, it contains a delta function. So at omega equals 0, the conductivity will be infinite. But its delta function has a weight in front of it. And turns out what you can show is this weight is actually inversely proportional to a certain thermodynamic susceptibility. So it's defined as follows. It's the derivative of the expectation value of the conserved quantity gamma with respect to eta. Remember, eta is the thermodynamic variable conjugate to gamma that appears in this ensemble, and gamma is the conserved quantity. So this is a kind of thermodynamic susceptibility. It's kind of analogous to the charge susceptibility, which would be like dq d mu. But here it's for this additional conserved quantity gamma. So if, sorry, oops, what am I doing? So if chi gamma goes to infinity, which can happen at a critical point, then the weight goes to 0. And in that case, you basically remove this delta function. So the DC conductivity and omega equals 0 will become finite. So that's non-zero resistivity. And so this is the sense in which you can non-zero resistivity due to critical fluctuations. The critical fluctuations drive this susceptibility to infinity. So that's the idea of critical drag. And we'll show some examples later on in the talk.
Is this a real part of conductivity only?
This is the real part. That's right. Of course, you can get the imaginary part from Kramer's quadrant, but the delta function is in the real part.
Okay. But in the imaginary part, there will be a pole corresponding with the strength fixed by omega. I mean, by W.
Yeah, I mean, yeah, that's right. Okay, so that was basically the overview. So this is the outline of the rest of my talk. I will give you this background on Hooft anomalies. I mean, many people in the audience probably are familiar with this, but for those who are not, I will explain what a Hooft anomaly is. And I will show an example. And then it turns out these anomalies are really the right way to think about these loopholes in Bloch's theorem that I mentioned before that leads to dissipationless current. And actually, they let you generalize Bloch's theorem to a more general version that actually incorporates these anomalies. And then I'll discuss some examples of that, including things which manifest as critical drag phenomenon that I mentioned. And finally, I will argue that there's some very general relations between dissipationless current and compressibility. Okay, so I want to talk about anomalies, and I will do this by way of an example, 1D Luttinger liquid. So 1D Luttinger liquid actually has an emergent symmetry. Microscopically, it just has charge conservation symmetry as a U1, but it actually has an emergent U1 times U1 symmetry, because in terms of a low energy theory, the left and right moving charges are separately conserved. So the left moving charge is kind of the charge that sits near this KL point. The right moving charge is the charge that sits near the KL point. And you can decompose the charge into the two kinds of charge, and each of them is separately conserved. So it turns out that this symmetry actually has an anomaly. And what that means is if you apply an electric field, then the left and right moving charges are no longer separately conserved. The total charge is still conserved, of course, but the left and right moving charges are no longer separately conserved in the presence of an electric field. And so there's a simple picture, at least in the non-interacting limit for this. In the non-interacting limit, your electrons just occupy single particle states. You apply an electric field, they feel a force, so they move in momentum space in response to this force. And as you can see, because the electrons are moving in momentum space, you get more electrons on the right moving side and less electrons on the left moving side. So the left and right moving charges are not separately conserved in the presence of this electric field, even though without the electric field, they were separately conserved. So another way to say this, if you introduce the total charge, which is the sum of the number of left movers and right movers, and then the axial charge is the difference between the number of left and right movers, then you can show that the axial charge is non-conserved in the presence of the electric field. And specifically, if you look at the continuity equation for the axial current, there's a non-trivial right-hand side proportional to the electric field, which is telling you that the charge is not conserved. The axial charge is not conserved. So this example of what we call a Hooft anomaly. So because you had a thing which was originally a symmetry and originally a conserved quantity, but you apply a background gauge field, and the charge becomes non-conserved. That's basically a more general statement of what a Hooft anomaly is. Maybe not the most general statement, but there is a class of Hooft anomalies that have this property, that you apply a background gauge field and the charge becomes non-conserved. So there's actually a very close connection between these anomalies and symmetry protected topological phases. So in order to explain why that's the case, let me try and find this anomaly that I had before, but here was an emergent symmetry, but I want to try to find a system that has that anomaly, but with respect to a macroscopic symmetry. So we want to find a system that has a microscopic U1 times U1 symmetry and that manifests this same anomaly structure. So maximum U1 symmetry, you can think of that as saying that the charge is conserved, and also you have a z component of spin that's also conserved at the same time. And so then if you want to realize this anomaly, what you would do is you would find a system with left and right moving modes, but such that the right moving modes carry only spin up and the left moving modes carry only spin down. So people sometimes call these helical modes. So if that's the case, then we can identify the number of left movers with the number of down spins and the number of right movers with the number of up spins. And so then this axial charge, which is the difference, you can basically identify just as the total spin, total SE component of the spin. And so this anomaly then, I mean, the system has the same anomaly as the previous one for the same reasons, basically. So this anomaly is telling you that the spin is non-conserved in the presence of an electric field. So then you can ask, can this ever actually occur? And the answer is no, it cannot occur in a one-dimensional system, in a purely one-dimensional system. But it can occur on the boundary of a two-dimensional topological phase. So if you have some gapped topological phase in two spatial dimensions, and then it can have a gapless boundary theory. And these helical modes, which tell you that you have a Hooft anomaly, can occur on the boundary of a bulk topological phase. So that's basically a general statement about Hooft anomalies. Hooft anomalies always occur on the boundaries of a symmetry protected topological phase in one higher dimension. So there's this kind of bulk boundary correspondence between Hooft anomalies in d spatial dimensions and symmetry protected topological phases in d+1 spatial dimensions. They're two sides of the same coin, if you like. And so in this particular example that I mentioned, where you have a U1 times U1 symmetry, like spin U1 and charge U1, the bulk topological phase you would want would be basically a quantum spin Hall insulator. And so we know that these quantum spin Hall insulators have these helical modes on the surface. So these helical modes are anomalous in the sense that they cannot occur on their own. They need to be on the boundary of a high dimensional topological insulator. But so this statement about you have to be on the boundary of a topological phase is true of the symmetry at play, which here was this U1 times U1 is a macroscopic symmetry. If you want the symmetry just to be if you want the symmetry to be an emergent symmetry, then you can have an anomaly even in a purely one-dimensional system. Here we had an emergent U1 times U1 symmetry, but a 1D Luttinger liquid obviously is a purely 1D system. So because the symmetry is emergent, that's why it's allowed to have an anomaly. But the structure of an anomaly is the same, whether it's an emergent symmetry or a macroscopic symmetry. So it can still be helpful to think about this higher dimensional topological phase to understand the anomaly. So let me just make some further statements about these two Hooft anomalies. First of all, they're kinematic properties, not dynamical properties. So what do I mean by that? For example, for this 1D Luttinger liquid where the axial charge is non-conserved in response to an electric field, that is basically equivalent to the statement that the local charge densities don't commute. So if you try to write the charge, which is the generator of one of the U1 symmetries, as the integral of some local density, and if you try to write the axial charge again as the integral of some local density, you can do that, but what you will find is that these local densities don't commute, even though the charge and the axial charge do commute. It's an abelian symmetry, but locally these densities don't commute. They have a contact term in the commutator with this delta function. So the statement that you have this non-conservation of a charge is not a statement about some particular Hamiltonian. Any Hamiltonian that lives in this Hilbert space where the symmetries act in this way will have the same anomaly. So it's really a property of the Hilbert space and the way the symmetries act on the Hilbert space rather than as any particular Hamiltonian. That's what I mean by kinematic property. More generally, if you go beyond these single component Luttinger liquids, you can have some anomaly coefficient here, m. So it's some number that appears in front of this delta function. It's the same number that would appear in this conservation law, or the violation of conservation law. So m is some number. It actually has to be an integer for consistency reasons. So this anomaly is actually quantized. Anomaly coefficient is quantized. So generally, that should always be true for these two Hooft anomalies, that they have quantized coefficients. So that was the background on the Hooft anomalies. And then now I want to move on and I will explain why these are relevant to this Bloch's theorem. So we have to go back and revisit the proof of Bloch's theorem So I'm going to follow in these papers. Let's, for simplicity, just consider a system, a one-dimensional system with periodic boundary conditions and length L. And in order to prove Bloch's theorem, we introduce this twist operator, defined in this way, where n of x is the local charge density. So this twist operator, appears in many contexts, and it has many names. You can think of it as large gauge transformation operator that inserts 2 pi flux through the circle. Sometimes it's also called a polarization operator. So if you're familiar with the proof of the Lifshitz matters theorem or Luttinger's theorem that uses these twist operators, and so it also plays a key role in the proof of Bloch's theorem. So what you can show about this twist operator is if you take the Hamiltonian and you conjugate it by this twist operator and then take expectation value, you get the expectation value Hamiltonian plus a term that's proportional to the expectation value of the current, plus additional terms that order 1 over L, so they go to 0 in the thermodynamic limit. This is really a manifestation, if you like, of the fact that you can define the current to be the functional derivative of the Hamiltonian in respect to the vector potential. And then we use the relation between these twist operators and large gauge transformations. So you can derive this equation. And then if you conjugate the charge operator by this twist operator, you get back just the same thing. That's essentially the manifestation of the fact that the charge should be a microscopic symmetry, so it shouldn't be anomalous. So now if we look at this grand canonical ensemble state, the grand canonical ensemble state satisfies a variational principle, which is that it's the unique state that minimizes the grand potential, which is like the H minus mu q minus T S, where S is the entropy. So if you use this variational principle, and then you consider you take this grand canonical ensemble state, you conjugate it by the twist operator, then use these equations, you immediately derive that the expectation value of the current in this state must be order 1 over L. In other words, it goes to 0 in thermodynamic limit. So this is the statement of Bloch's theorem. But now what I said before was that we want to consider this generalized ensemble that takes into account the additional conserved quantities. So now we also need to know how does this gamma transform into this twist operator. Unlike the other things, it might not be, unlike the charge, it might not be invariant under the twist operator. So you conjugate the twist operator, you could get some extra number. And then if you repeat the argument for Bloch's theorem, what you'll find is that the current is actually equal to eta, which is this thermodynamic variable, times this number psi. So this is kind of generalized Bloch's theorem. Rather than saying that the current has to be 0, it's saying that the current has to be non-zero. It's completely determined by this eta and by this psi. So if eta and psi are non-zero, then the current not only can be non-zero, but actually must be non-zero. So that's the loophole in Bloch's theorem, that if you have this conserved quantity that doesn't commute with the twist operator, then it can give you a non-zero current even in equilibrium. Okay, but how do we interpret this statement about the gamma and not commuting with the twist operator? So by way of example, suppose that gamma is a generator of infinitesimal translation symmetry, which is to say that it's the momentum. Then by direct calculation, what you'll find is that the psi is equal to the expectation value of the charge density. And then on the other hand, this thermodynamic conjugate variable eta, if gamma is momentum, then eta has units of velocity. So you can actually identify this eta as being the drift velocity v. So it's just the overall drift velocity of the system. So then from this formula, you'll find that the current is equal to the charge density times the drift velocity. Maybe that's not too shocking of an equation, but we've derived it in a very general way now using these Bloch's theorem arguments. And in particular, the current can be non-zero. So that's the reason why the momentum conservation can protect the current. As we saw, for example, in this continuous electron gas in the continuum. I don't want to say too much more about this. I mean, generally, the systems we're interested in condensed matter are on the lattice, so they don't have a continuous translation symmetry. So this discussion would not be applicable. So instead, let's imagine that gamma is instead the generator of an internal U1 symmetry. Then what I can show is that gamma is just the anomaly coefficient. So if we have a U1 symmetry generated by gamma, and then we always have a U1 symmetry generated by the electric charge, we have two U1 symmetries, they can have a mixed anomaly, which is to say you apply an electric field, which is a background gauge field of a charge, and the charge of the gamma charge becomes non-conserved. So that's already what, this is exactly the equation that we saw previously in the 1D Luttinger liquid. And so how do you show that this anomaly implies this equation for the twist operator? Basically, you just use this fact, which I mentioned before, which is that this anomaly is equivalent to saying that the local densities don't commute, this delta function. And then since the gamma can be written as the integral of the density n gamma, and this u was also defined in terms of the density n, just directly from this equation, you will compute that gamma is equal to n. So yeah, so it's the coefficient of this mixed anomaly that's telling you what the potential non-zero value of the current is. So in particular, this Luttinger liquid in 1D, because it precisely had this mixed anomaly structure, supports dissipationless current. So the resistivity is 0. So you can get finite resistivity in Luttinger liquid, but that comes from irrelevant perturbations that would violate this emergent symmetry. So emergent symmetry kind of means that any perturbation that breaks the symmetry has to be irrelevant in the RG sense. But nevertheless, irrelevant perturbations can still give you finite resistivity at finite temperature. But if you just focus on the renormalization group fixed point theory, where you have this emergent symmetry, then the resistivity is exactly 0, and it's protected by this emergent symmetry and mixed anomaly structure. So let's come back and say, what does
Dominic,
this have to do?
Can I ask a quick question about that?
Oh, yes.
I want to make sure I understand. So I thought, let's say just a simple impurity in a Luttinger liquid could be a relevant perturbation that kind of cuts the chain and it would clearly produce resistance.
Yeah, so in that case, by emergent symmetry here, I meant it's, all the perturbations to break a symmetry are irrelevant if you consider a clean system. So if you have disorder, that can violate asymmetry as well, and that would that would also give you non-zero resistivity.
Okay.
But in a clean system, the resistivity only comes from the irrelevant terms. So let's come back and say, what does this have to do with the conductivity? So to explain that, I'm going to take some system as a function of time. So let's assume that originally there's no current in the system. And now at time t equals 0, I'm going to apply an electric field impulse. So it's basically electric field that does a delta function as a function of time. So that will immediately generate some current. And maybe as time goes on, the current will relax. But let's imagine it goes to some value j infinity at late times. So if we define a W to be the ratio of this late time current j infinity to the original electric field impulse that you applied, then by some Fourier transform, you'll see that this W is precisely giving you the weight that sits in front of the delta function in the AC conductivity. So in general, the weight could be non-zero if j infinity is non-zero. And why can j infinity be non-zero? Well, we assume that the system reaches equilibrium at late times, but nevertheless, you could still have non-zero value current because of these Bloch theorem arguments or loopholes in Bloch theorem that I discussed. So let's suppose you have some conserved quantity, which we call gamma, and the eta was the thermodynamically conjugate variable. Then this generalized Bloch theorem argument told you that you can actually exactly compute what the current must be. It's just equal to the anomaly coefficient times this thermodynamic variable eta. And so what is this thermodynamically conjugate variable? Well, originally we were assuming it was 0 because there's no current and the current is proportional to eta. But when you apply an electric field, at late times, the equilibrium state could have a non-zero value of eta. And so you can express the new value of eta in terms of the change in the exploitation of the value of the conserved quantity gamma. And this equation basically is the definition of the thermodynamic susceptibility chi gamma gamma. And then what is the change in the expectation value of gamma? Well, the only reason why gamma changes is because you applied an electric field, because otherwise it was a conserved quantity. But as I said, one of the manifestations of the anomaly is that you apply an electric field and the gamma becomes non-conserved. And so while you're applying the electric field, which is only at time t equals 0 from this delta function, gamma can change. And then after it's changed at t equals 0, whatever value of gamma you've gotten, it will just stay the same because now you've removed the electric field, and so the gamma is conserved again. And so therefore we can show, because the change in gamma just comes from the electric field at t equals 0, and the fact that the gamma has an anomaly. From the anomaly equation, you can conclude that the change in gamma is proportional to the anomaly coefficient and proportional to the electric field impulse that you applied. So combine all these equations, and we have this definition of a weight. You'll conclude that a weight has the following formula. So it's proportional to the anomaly coefficient squared, inversely proportional to the thermodynamic susceptibility. So the statement I stated earlier in the talk that this weight of a delta function is inversely proportional to susceptibility. So indeed, you see that that's the case. And so if you send the thermodynamic susceptibility to infinity, which could occur at criticality, if the weight goes to 0. So that's the mechanism by which you can have non-zero resistivity due to the critical fluctuations. So is there any other way to get the weight to 0? Well, I guess you could say the anomaly coefficient could be 0. Remember, the anomaly coefficient is some discrete thing, though. It's quantized. It's not like it's something you can just tune to 0 willy-nilly. I mean, so either it's 0 a weight to be 0 would be to have these critical fluctuations that drive it to 0 from the susceptibility. So maybe I should mention that you will sometimes see people write formulas that look kind of like this, but they, in the numerator, they have this chi j gamma squared. So you will see formulas like this in the literature on hydrodynamics or memory matrices and stuff like that. And so chi j gamma is like a cross susceptibility between the current and this conserved quantity gamma. So this formula is correct, but actually this cross susceptibility is completely determined by the anomaly. It's not some dynamical quantity. It's completely fixed by the anomaly. I'm not sure to what extent this was appreciated previously, but anyway, from this generalized Bloch's argument, you can show that that's true. So let me give you another example. I already told about this 1D Luttinger liquid, but now I'll give you a two-dimensional example, which is a superfluid. So superfluid, as we know, you have some boson that condenses. The low energy physics would be described in terms of the phase field of a boson. So you have an action that would look something like this, for example. And if a superfluid, we know it has a dissipationless current, famously, and dissipation current is proportional to the gradient of its phase field. And it is constant in proportionality is a phase stiffness that appears in the action. So if it has dissipationless current, we have to explain what is the symmetry that protects the current. Okay, so this is what I'm answering now. The symmetry that protects the current is actually this winding number. So if you take some, imagine we put the system on a torus or something, you can take some non-contractible cycle over the torus and then integrate the gradient of theta over that cycle. That defines a winding number over this cycle. And this winding number is actually a conserved quantity, because the only way that this winding number could change as a function of time would be if you have some vortex, and the vortex crosses this curve. But in the superfluid phase, vortices are actually confined. So there are no vortices. So in the superfluid phase, this is really a symmetry. So it's as we were discussing before, it's an emergent symmetry of the system, but it's a very good symmetry. Well, really an exact symmetry in the superfluid phase. So this is actually an example of something that we call a one-form symmetry. The spatial dimension d equals 2 is a one-form symmetry. In general, it would be like a d minus 1 form symmetry. But let's just focus on d equals 2. So the reason for that is that basically a conventional symmetry, which is what we would call a zero-form symmetry, the conserved charge would be some density that you integrate over all of space. But here, instead of integrating over all of space, you're just integrating over some one-dimensional curve. That's essentially what it means to have a one-form symmetry. And there's another important aspect of a one-form symmetry, which is that suppose we take two different curves, but suppose they are continuously deformable into each other. So they represent the same homology class, if you like, on the torus. Then the winding number associated with these two curves is actually the same. And that's a statement not just about the expectation of value of a winding number. If you actually look at how the operator acts on the Hilbert space, I mean the Hilbert space of in the superfluid phase, it's actually the exact same operator. So identically the same operator, even associated with different curves, as long as they are deformable into each other. So again, that's a consequence of the absence of vortices, because the only way these operators could be different would be if there's some potential for there to be a vortex in between. But in the superfluid phase, there are no vortices. And so in particular, if you take a contractible curve, that winding number would be identically 0. Maybe I should mention, I mean, I guess Caltech is kind of the center of the fractal universe. And sometimes in the fractal literature, I've seen people use the term one-form symmetry to indicate that you integrate over one-dimensional curves, but they don't impose this topological deformation condition. Yeah, so I don't subscribe to that terminology. For me, one-form symmetry always includes this topological deformation property. That's a really important part of a one-form symmetry for me. So it can be kind of confusing to have to think about these global quantities, like you have to reduce some non-trivial topology, like on a torus, and you consider these non-contractible cycles. So it's helpful also to think about one-form symmetries in terms of local physics. And so this is something that we can generally do. I mean, it's also something you can do for conventional zero-form symmetries. For a zero-form symmetry, you have some space-time current. So it's just a space-time vector where the time component is the charge density and the spatial component is the spatial current. And then this space-time current satisfies the continuity equation, which you can think of as a statement of local charge conservation. So this is certainly implies that the total charge, which is the integral of the density, is conserved, but maybe it's a more powerful statement, actually. It's a stronger statement. It's local charge conservation. So for one-form symmetry, you can also do something similar, but you have to introduce an anti-symmetric rank 2 tensor, which we call the current tensor. So certain components of these rank 2 tensor, specifically the 0i components that sit over here, are what we identify as a one-form charge density. So this is a thing that you would integrate over these one-dimensional curves to get the global one-form charge. And then the statement of local conservation of one-form charge is just, again, that this space-time tensor is divergenceless. And so, for example, in a superfluid, what you would do is you would just define this space-time tensor in this way in terms of the derivative of the phase field. And then you can immediately see if you take the divergence of that, then it's 0 because you have d mu and d lambda, but then you anti-symmetrize from this resistivity tensor. So it just gives you 0 as long as there are no vortices that would make the theta field be singular. So if there are no vortices, which is the case in the superfluid phase, then this local charge conservation is identically satisfied, as you would hope, because you have this one-form symmetry. So this one-form symmetry actually has a mixed anomaly with the electric charge. So this continuity equation for the one-form charge is actually evaluated in the presence of the electromagnetic field. So we have this anomaly equation that involves the electromagnetic field strength tensor. So you're applying a background gauge field for the U1 global symmetry, the electric charge U1. This one-form symmetry actually has a non-conservation. So that's a mixed anomaly between the electric charge and this one-form symmetry. So then you can repeat all the arguments I gave previously that this emergent symmetry has a mixed anomaly is going to give you a loophole in Bloch's theorem. And so allow you to carry dissipationless current. So interesting side note, if you really want to do this argument properly, you have to say what is the thermal equilibrium state in the presence of a one-form symmetry. So there's a nice answer to that. You can find this by invoking a variational principle. You want to find the state that maximizes the entropy subject to the constraints that you fix the expectation values of the conserved quantities. And so the answer turns out to be this state like this. So Ni here is the one-form charge density. It's just proportional to the gradient of the phase field for a superfluid. And its eta I is some thermodynamic quantity that we introduced, which is the conjugate to the one-form charge. And it's actually, we can call it the one-form chemical potential. So it's some vector field on space. And if you want to really to have it, say it's globally in equilibrium, this vector field has to be curl-free. Another way to say it is a closed one-form. So this, you can think of this as the analogous statement to if you have a zero-form symmetry, you want to be globally in thermal equilibrium, the chemical potential has to be a constant function of space. But here, it's not that it has to be constant, it just has to be curl-free. And so then you can repeat a similar argument to what I gave earlier with this Bloch's theorem argument And so you get the generalized Bloch theorem that applies in the presence of one-form symmetries, that the current is proportional to this one-form chemical differential, and proportional to the m here again is the anomaly coefficient. So it's the general the quantity that appears in this equation. For a superfluid, it's just m equals 1. And then you can also repeat. Oh yeah, and so by the way, if you take the divergence of this equation, you'll see that the divergence of the spatial current is 0 because of this curl-free condition. So that's nice to see, because in equilibrium, the spatial current has to be divergenceless. So that's good. So then you can also compute the conductivity tensor, or at least the singular part at omega equals 0. So again, you find that this one-form symmetry can protect the dissipationless current, which manifests in this non-trivial weight that appears in front of the delta function. So here is which is the conductivity tensor now. And so this weight can be written in terms of this formula. So proportional to the anomaly coefficient squared, as we already saw before, and proportional to the inverse of the susceptibility. And the susceptibility here we would define the susceptibility matrix, which is the derivative of the one-form charge density with respect to the one-form chemical potential. So that's again a kind of thermodynamic susceptibility. So you invert this matrix and then it appears in this formula. So again, if you want to have a dissipationless current or non-zero if you want to have a non-zero resistivity, you would want to either have the anomaly coefficient be 0, or you'd want the susceptibility to diverge. So now in the superfluid, of course, this is a free theory, so you can just compute the susceptibility exactly. And it turns out it's just inversely proportional to the phase stiffness. So in a superfluid, phase stiffness should be finite and non-zero. So the superfluid so the susceptibility is not diverging. So then you just get some finite weight in front of the delta function. In particular, set omega equals 0, the resistivity is the conductivity is infinite, so the resistivity is 0. Of course, that's what it should be for a superfluid. But now suppose we want to find an example of a system where the susceptibility does diverge. That would be this critical drag mechanism that I gave you. And so that would allow you to restore a non-zero resistivity due to critical fluctuations. So you could imagine that you send the phase stiffness to 0, then the susceptibility would diverge. So that's actually what's going to happen in the next example. So example 3 is what I call a quantum Lifshitz model, and this actually will be an example of this critical drag phenomenon that I mentioned.
So you mentioned this example where in the case of superfluid, you have a current associated with the one-form symmetry, and there's a mixed anomaly for that current. So is there an example where you can have a dissipationless current associated with the one-form symmetry due to like a mixed anomaly associated with the current for let's say a two-form symmetry or higher?
You're saying does the can you have a dissipationless current off a one-form charge?
Yeah.
That's the question. That's a good question. Probably yes, but I mean the mixed anomaly goes both ways. Like I wrote this equation, but it's also true that the zero-form charge would be non-conserved in the presence of a background gauge field of a one-form charge. Yeah, so it's probably true that there's some dissipationless current in certain circumstances because of that, but you have to make sure that the anomaly structure is appropriate to get that. I haven't thought about that carefully, but probably you can have something like that. Okay, so I'm going to talk about this quantum Lifshitz model. So the quantum Lifshitz model is similar to a superfluid, but we take the phase stiffness and we send it to 0 to get rid of this term. If we're going to do that, we have to introduce some high derivative terms to regularize the theory. And so this basically defines a quantum Lifshitz model. So the quantum Lifshitz model is actually not a superfluid in itself. If you the global U1 symmetry is not spontaneously broken in this quantum Lifshitz model. But you can think of it as a phase transition between two superfluids. So if you have a superfluid at 0 momentum, where the derivative of the phase field is 0 in the ground state. superfluid at non-zero momentum where derivative phase flow is non-zero in the ground state. So it's a zero momentum condensate, non-zero momentum condensate. The quantum Lifshitz model basically describes the continuous phase transition between these two superfluids. So it's like a critical point between two superfluids. So in this quantum Lifshitz model, the vortices are still gapped. They're not logarithmically confined as they are in the superfluid, but certainly they're gapped. So if your energy scale is below the vortex cap, you still have a emergent one-form symmetry. It's the same one-form symmetry that a superfluid has. And it has the same mixed anomaly with the electric charge. But now if you compute the conductivity as a function of frequency, you actually see that it's just zero. You can compute that, I mean, that's easy to compute just from this action. It's just zero for all frequencies, and there's no delta function. So then you can ask, what happened to this delta function? We still have this one-form symmetry. Why doesn't that give you a dissipationless current even to a delta function? And of course, the answer, as I already hinted at, is that the delta function is suppressed by criticality because this quantum Lifshitz model actually has divergent susceptibility of a one-form charge. So the critical fluctuations associated with this critical point between the two superfluids are actually suppressing this delta function. So that's resistivity because of critical fluctuations. That's what we call critical drag. So this is a very simple example of this phenomenon. So let me mention now, there's a general connection between this dissipationless current story and compressibility. So what do I mean by compressibility? I define a system that has lattice translation symmetry to be compressible if the charge field in nu, which is basically just the electric charge per unit cell, is continuously tunable without qualitatively changing low energy physics. So generally, this property is true for metals. It's also true for superfluids. So maybe this is a slightly unfamiliar definition of compressibility. Often people just find compressibility to mean that dn d mu is non-zero, where n is the charge density and mu is the chemical potential. So if dn d mu is non-zero, people say it's compressible. But here I'm using this definition, which is a little bit different. It's kind of related, but it's not necessarily always equivalent to that other definition. But it's the definition. This is the definition I will use today. And then I will define a system to be flexible if it has an emergent symmetry and anomaly such that it leads to a Lippold and Bloch theorem. So we saw, we saw in some examples earlier on how emergent symmetry and anomaly leads to Lippold and Bloch theorem. I maybe didn't say the most general statement of what circumstances that occurs in, but I will just define this flexibility condition to be the most general situation in which emergent symmetry and anomaly leads to a Lippold and Bloch theorem. And then I have this conjecture, which is that if you have a system with lattice translation symmetry, so no disorder, then flexible and compressible is equivalent. So compressible implies flexible, flexible implies compressible. So why should this conjecture be true? Well, first of all, compressibility is closely related to emergent symmetries and anomalies, as we emphasize in this paper that I wrote with Ryan Flogren and Sentil. And so flexibility is from the definition clear that it involves emergent symmetries and anomalies. Compressibility is also actually closely related to emergent symmetries and anomalies. So that starts to indicate why there would be a connection. And then we were actually able to use this connection to actually give a proof of this conjecture for one-dimensional systems. In higher dimensions, we don't have a proof, but it's probably true. One argument would be that if you take a two-dimensional system, you could just compactify one dimension and it becomes quasi-one-dimensional, and you invoke for one-dimensional proof. Maybe that argument's not totally rigorous, but in any case, it's very suggestive. So I think that this conjecture should be true in any spatial dimension. Maybe we can point out that this conjecture is actually satisfied by all currently known states of matter. So superfluid is flexible for the reason I described, the Lippold and Bloch theorem comes from the anomaly of a one-to-one symmetry. So superfluid is also compressible. The same is true for this quantum Lifshitz model that I just mentioned. Fermi liquids, didn't talk too much about Fermi liquid, but Fermi liquid actually has an infinite dimensional symmetry group. The charge associated with each point of a Fermi surface is conserved. And so this thing has an anomaly that actually protects the current. So this Fermi liquid is flexible. It's certainly also compressible. Because the filling of a Fermi liquid is just a volume enclosed by the Fermi surface. That's Luttinger's theorem. So you can just deform the Fermi surface and change the filling. So Fermi liquid is compressible. And then in this paper, we also discussed a general class of non-Fermi liquids that we call ersatz Fermi liquids. So ersatz Fermi liquids are non-Fermi liquids, but they have the same emergent symmetry and anomalies as Fermi liquids, so therefore they're also fluxible and compressible. And we kind of argued that most, if not all, non-Fermi liquids would actually be ersatz Fermi liquids. So this statements are also true maybe for all non-Fermi liquids. So then a band insulator is not compressible because there's this Lifshitz matter theorem that says that band or mod insulators or any kind of insulator can only occur at integer fillings. So you cannot tune the filling, it's just pinned to be an integer. So band and mod insulators are not compressible, and they're certainly not fluxible. I mean, in the low energy theory of an insulator, there is no electric charge, so there's no way for it to have an anomaly of anything. So it's not flexible. Semi-metal is also neither flexible nor compressible. The composite Fermi liquid is the trickiest one. Composite Fermi is not. So this is the system that occurs at nu equals 1/2 in the quantum Hall effect. So you can just describe it by some flux attachment procedure. So it's actually not compressible because it's pinned to nu equals 1/2 in this quantum Hall systems. It's also not flexible, which maybe is a little surprising because it does have a infinite dimensional emergent symmetry group, but I don't think that the anomaly protects the current in this case. And also there's no infinite conductivity in a clean composite Fermi liquid. If you think about the longitudinal conductivity, it's actually just 0. And the transverse conductivity is E²/2h. So there's no delta function in the conductivity. So that makes sense. Okay, so all these states of matter satisfy this conjecture. So if you don't believe these hand-waving arguments about you invoke for 1D proof, you would at least have to come up with some new state of matter that violates, that is different from any of these. And this is pretty much all the states of matter that we know of. So that might be difficult. Dominic? Yes.
I thought for a composite Fermi liquid, at least the usual DN/d mu definition would give.
Yeah. So that this is an instance in which the DN/d mu definition is not equivalent to this definition.
Yeah. So can you? So that definition is just words. Can you restate that in terms of some kind of mathematically computable property of the composite Fermi liquid?
Well, if you use this filling framework that we developed, then it becomes a precise statement in terms of the emergent symmetry and anomaly. I don't know if that answers the question. I mean, you have to think about what the emergent symmetry and anomaly of the composite Fermi liquid is. Although, I think we understand what it is. I don't know if that answers the question.
Well, in particular, there is this, without qualitatively changing low energy physics, and I don't know if there's some subjectivity to the word qualitative there. And I'm kind of looking for some more unambiguous.
I guess the unambiguous definition would be without changing the IR fixed point theory. You get the same IR fixed point theory, even at different densities or different fillings. That's maybe a more precise statement.
Okay, thanks.
And so just to, so Jason, the composite Fermi liquid, of course, lives at nu equals 1/2, for instance. So if you change the density without changing the magnetic field, you leave the composite Fermi liquid, right? So it's tied to the flux density. The charge density is tied to the flux density.
Yeah, I see. I guess I was, thinking about, moving away from the equals 1/2 as kind of inducing just quantum oscillations in the composite Fermi liquid, and in some rough sense, it feels like sort of the same state. But I see your point.
If you really exact with 0 temperature and no disorder, you have this whole chain sequence that approaches the nu equals 1/2. So you have an infinite sequence of gaps that are opening and closing. So you can't really say that it's just the same low energy physics.
I see. Yeah, and maybe also the translation symmetry is important. I guess I'm probably implicitly thinking about a situation where you have disorder and things that can probably mask a bit the singular behavior with changing nu that you have in mind.
Yeah, that's probably true. Yeah, but so with translational symmetry, you can prove that nu has to be 1/2, but that disorder maybe changes that.
I see. Thank you.
Okay, so let's sum up what have we learned. So I started by asking what causes the resistivity to be non-zero, but then I said that we should turn this around and say what causes the resistivity to be 0, because like non-zero resistivity is a default from this box frame. You have to somehow find a loophole in that if you want 0 resistivity. But maybe we should turn it around again now, because if you have a system that's clean and compressible, and if you believe this conjecture I just stated, that a clean compressible system also must be flexible. So therefore, it has this emergent symmetry and anomaly that protects the current. So then 0 resistivity would now be the default in these clean compressible systems. So then you can ask, what would cause non-zero resistivity then? Well, either you can consider RG irrelevant couplings that break the emergent symmetry, which is what happens in Fermi liquids. So in a clean Fermi liquid, the resistivity would come from Umklapp, but Umklapp is actually irrelevant in the fixed point of the Fermi liquids. At finite temperature, though, it can give you a non-zero resistivity. But if you want to get resistivity that occurs in the RG fixed point theory, that's not rather than being caused by irrelevant perturbations, the only way is this critical drag mechanism where you have a divergent susceptibility that suppresses the weight of the delta function. So that's the only way to get non-zero resistivity in the fixed point theory. So that's a very strong conclusion. And it's particularly relevant for these strange metals, because in strange metals, what you see in the experiment is that there's this scaling form at low temperatures. If you look at conductivity as a function of frequency and temperature, it has a scaling collapse where the function of two variables is expressed in terms of a function of a single variable, a scaling function sigma, and specifically sigma 0 is finite. The only way to interpret the scaling form, as we tried to argue in our papers, is that this scaling function sigma really represents the conductivity of the fixed point theory. And in particular, since sigma 0 is finite, you conclude that the conductivity of fixed point theory is finite. So how do we reconcile that with this statement? It seems like the only way to get non-zero resistivity in fixed point theory is from critical drag. So if you believe that strange metal is clean and compressible, which we probably should believe, of course, there's always disorder, but if we believe that the strange metal could occur in a totally clean system, which I think you can argue why it probably is the case, we have this very powerful conclusion. We don't know what the theory of a strange metal is, but whatever it is, it has to exhibit critical drag. So we've learned something very strong about this strange metal. Okay, so that brings me to the end. So by these general resistivity arguments, we can understand a lot about resistivity even without a specific model. We can understand that resistivity could be caused by critical fluctuations. And in particular, this must happen in the strange metal. Okay, so that's my conclusion. Thank you for listening. So yeah, I guess it's questions, or are we supposed to take a break? What happens now?
Yes, quick question, just because your previous slide was a strange metal. When you say critical, what exactly? The RG fixed point supposed to t equals 0, right?
Yeah, right. Well, it doesn't have to be. RG fixed point is just a vector of couplings. So you can take the Hamiltonian that's characterized by some set of couplings and consider the thermal state of that Hamiltonian. That's something you're allowed to do. So that's what we mean by the. So you can actually talk about an RG fixed point at finite temperature. So that's what I mean by
positive temperature. So yeah, so when you refer to, so you refer to positive temperature behavior, the limit of 0 omega, 0 momentum, and fixed temperature.
Yeah, well, so this scaling form should kind of be an asymptotic statement as you take omega and t to 0 while the ratio is held fixed. But yeah,
want to take omega to 0 faster than t, so that's where the sigma of 0 becomes important. So it's non-zero, right? So you're talking about the limit of omega goes to 0 and saying that.
Yeah, so sorry. So in this statement where you interpret the scaling function as a conductivity of a fixed point theory, so that would be the conductivity at just at some fixed temperature. Yeah.
So can you repeat again the statement that because they're compressible and supposedly translation invariant, then this must come from what is it? What should be then happen to ensure this kind of behavior in the conductivity? What's critical drag? In other words, can you remind us?
It's this statement that the susceptibility diverges, and that suppresses the weight of the delta function in the conductivity. So what's the slides of this?
But the susceptibility of what? We don't know, or
well, it's a susceptibility of the conserved quantity. So then you have to say, what is the conserved quantity for a strange metal? I mean, that's an important question to ask. It's probably, I mean, so in a Fermi liquid, the conserved quantities is just the charge on each point of a Fermi surface. So in a Fermi liquid, that's what it would be. And probably, I mean, I don't have a proof, but I think it's very likely to be the same in a strange metal. Like you would still have a Fermi surface. Well, we know there's some kind of Fermi surface. I mean, we see that in the experiments. I mean, but it's not described by Fermi liquid theory. But nevertheless, I think there's still probably a conserved charge associated with each point on the Fermi surface. So that would be the susceptibility of these charges on the Fermi surface is a thing that would have to diverge. I should say that generally when a susceptibility diverges, it kind of susceptibility of all quantities in the same symmetry sector diverge. So although, I mean, this statement is just that the susceptibility of the charge on the Fermi surface diverges, really what we expect to happen is that susceptibility of anything in the same symmetry sector would diverge. So any operator that has the right symmetries, it actually has to be odd under the time reversal symmetry and odd under inversion symmetry. Any operator that's like odd under these time reversal and inversion symmetries would have divergence susceptibility.
Okay, thank you.
So you're thinking of this strange metal as like this ersatz Fermi liquid that you proposed?
Yes, I mean, I don't have a proof that a strange metal is an ersatz Fermi liquid, but it's a good guess. If it's not an ersatz Fermi liquid, it has to have some other conserved quantity, at least if you believe this conjecture I formulated. But it's kind of hard to imagine how that would work. I probably it's just an ersatz Fermi liquid, but I can't prove that.
Are there other to be the only way to get to non-zero resistivity, like strange metals?
Sorry, you kind of cut out for a part of that.
Oh, similar, just like strange metals, are there other systems where you expect critical drag to be the driver for non-zero resistivity?
Well, of course, I mentioned these quantum Lifshitz models, which may occur. There's some discussion that Cento has had recently that it may explain certain phenomenon in multi-layer graphene systems. Yeah, so what other context would there be? I mean, yeah, I mean, this strange metal is seen in quite a few materials, not just in cuprates, also heavy fermion has a similar behavior, so you would also apply there. I think generally when you do have this critical drag, you expect conductivity to scale with some like superlinearly, it would either be T linear or it would be like T to the 2/3 or something, some exponent less than 1. So we don't see that in too many materials. I mean, we see T linear in quite a few, which is kind of what we call strange metal. But anything where you see conductivity at scales like slower than linearly, I would have to attribute that to this critical drag, but I don't know when that would happen.
I guess one general question which I'm wondering about, maybe it's not too relevant, but here you try to generalize the Bloch theorem by choosing like these conserved quantities, which are in particular relevant for having a dissipationless electric current. But it seems like this phenomena could be more general, like you could have some other kinds of conserved quantities that lead to, different equilibrium conserved quantities. Like in this case, it's the current, right?
I'm not sure. I mean, you can talk about other kinds of transport, like thermal transport. Is that the question?
Yeah, I guess it was more of a comment that it seems like you could consider more general conserved quantities which lead to other like conserved equilibrium properties. Like here you had the dissipationless electric current, right? But in general, perhaps you could have more exotic conserved quantities, like we were discussing in the middle of the talk, where you could have like a conserved current associated with the one form symmetry. So something like that, but you would get those conservation laws once you have some more exotic conserved quantities appearing in this row equilibrium, which you use to generalize the Bloch theorem.
Yeah. I mean, whatever conserved quantities you have, you talk about its anomaly structure, and you can have analogs of that. But I mean, the really interesting thing would be to talk about thermal transport, because any system has conservation of energy. So what does this critical drag imply for thermal transport? It's also kind of confusing, because thinking about anomalies for energy is always a very difficult subject. But it would be very good to look at.
They're talking about energy transport. So in your discussion, did you assume that somehow phonons are not there in this whole discussion and they don't couple to your?
I mean, I did when I was talking about this conjecture about the lattice translation symmetry. I mean, otherwise I mean, these arguments kind of don't really care about phonons, except in as much as you, if you want to talk about a system with a lattice translation symmetry, then you kind of have to assume that the lattice is fixed, so there's no phonons. But otherwise, these general arguments, I mean, you can put the phonons in if you want.
Just like wondering if as part of the temperature. Okay, so if you have translational symmetry, you got to have phonons, right? And at positive temperature, they'll be coupled to your. Okay, so this discussion just includes phonons, right? So it's some just current and some effective field theory of electrons and phonons. So there's nothing special about. So they're included, right? So they just don't.
Yeah, I mean, if you're going to include phonons, you have to say that there's a continuous translation symmetry, because I mean, otherwise the phonons wouldn't make sense. So then, that would be one of the conserved quantities you have to consider in this analysis. So then you have to talk about the susceptibility of the momentum, which is actually kind of related to mass. So because ions are very heavy, they actually have the susceptibility of momentum is actually very high, which is maybe not infinite, but if you have a very large susceptibility and then even a little bit of disorder, it'll the weight is already very strongly suppressed, and then the disorder just smooths it out until you don't see it.
Okay, so you don't need to include phonons in this. You can just treat the ion as a fixed background. for the discussion.
Yeah, I mean, you don't have to. That was the question. Do you have to include phonons? Is that the question? I mean, yeah. I mean, it is. In many cases, it's valid to just ignore the phonons. If that was the question.
Yeah, because if you did, you would have at least U1 charge and also momentum, so you have more conservation laws to worry about.
Yeah. Yeah, generally, the conservation of continuous momentum doesn't have a huge impact on the system, basically because the ions are so massive.
Okay.
If you have very, very clean systems, then momentum conservation may start to be important. That's this phonon drag that people talk about.
Yeah, it's not important for charge transport, but it will be important if you discuss thermal transport. Yeah.
Maybe, yeah, I haven't thought too much about thermal transport.
All right.
Yeah, does anyone have any further questions? Okay, feel free to stay back if there are questions. If not, we should thank Dominic for the very nice talk. Thank you all for coming.
Thanks, Dominic, for the great talk.
Thanks.
Okay. Yeah, great. All right. Yeah, thanks, Dominic. Yeah, I think maybe I didn't clarify. Oh, sorry. Maybe I should stop there.